In these slides, we want to introduce the concept of electric flux, and it's actually a bit tricky, the idea. So let's try and motivate it from something we're going to do later on. Later on, we're going to say, what if you want to make a surface like this surface in space, and you want to calculate the current through this surface? So imagine you have charges. In this region, you have positive charges moving with a certain velocity, and here you have negative charges moving with a certain velocity. So the surface could have different charges moving in different regions, different locations, going across the surface in any direction you want. We make the area vectors the same way we discussed the idea of area as a vector, the usual way. It's perpendicular to the surface. And if you want to calculate the current through this surface, you're going to actually evaluate an integral of this form. We'll discuss this in detail, of course, in a future chapter. You're going to calculate something called J, current density, and J for negative charges is opposite the velocity. For positive charges, it's in the same direction as the velocity vector, and it doesn't matter. In general, you're going to calculate this J vector, and the J is related to the velocity in some way, and other things too. But you're going to integrate a certain quantity which involves getting J dotted into the area and summing this over the whole surface. So this is very similar to the kind of integral we're going to be doing in this chapter in Gauss's law. And in Gauss's law, you have integration of E dot dA instead of integration of J dot dA. So it has the same mathematical form. So we're just trying to motivate the mathematical form, but also to motivate another thing. In the case of current is something you can imagine. You can imagine we're calculating the rate at which charges cross the surface. So it's dq by dt. We know what it means. So there's something flowing through the surface, and we can visualize this and understand what it means. When we come to talk about electric flux, we don't have that leisure. The concept of electric flux is much more abstract. So for instance, let's take any general mathematical surface. In this case, it's an open surface. And as we said before, the area vector at different elements of area point perpendicular to the area. And for an open surface, we have a choice to make the area vector this way or this way. And I choose just to make it this way for this particular problem. Now, if we, in addition to this mathematical surface that doesn't exist in reality, if we have a charge distribution in space, like this one over here, then you'll also get an electric field at every single point in space. So that means the center of each square, the center of each element of area on this mathematical surface, now I can define two vectors. One is the electric field vector, and one is the area vector. And there's a certain angle between these two vectors, which we'll call theta. Now, electric flux delta phi for a particular element of area is defined to be the electric field at that element of area dotted into the area vector. And of course, the dot product between two vectors is just the magnitude of the first, the magnitude of the second, times cosine of the angle between them. So this is a quantity, it's a number. The dot product between two vectors is just a number. So it's a number, and it's called the electric flux. And now this is where the issue of the motivation comes from. This is an abstract quantity. It doesn't represent the flow of anything through the surface. There's nothing flowing through the surface. So it's a very abstract quantity. As we said, it's a number, so it can be positive, negative, or zero. The dot product between two vectors can be either positive, negative, or zero. So depending on the angle the electric field and area are relative to each other, this quantity can either be positive, negative, or zero for each element of area. Now, let's define something called the total electric flux through the whole surface. And you do that by summing the electric flux through each element of area and taking the limit when the area shrinks to zero. That means you're getting integration of E dot. That's what integration of E dot dA means. That's what this surface integral means. You're cutting up your surface into very small elements of area tending to zero in size, and you're getting E dot delta A for each element of area. So you're getting a number for each element of area, you're getting a number. And then you're adding all these numbers up, and it'll give you in the end a total number. And this total number could be zero, it could be positive, it could be negative. So again, why are we talking about electric flux? Why is this quantity important? Remember, because it's used in Gauss's law. And why is Gauss's law important? Because it's one of the four equations that are always correct. So that's the reason, the motivation why we're studying the concept of electric flux. And as part of the motivation, you have to start to get used to dealing with abstract concepts that you don't necessarily have to relate to familiar ideas. As I mentioned, we can give an analogous situation where you have the current, for instance, through a surface. It has the same mathematical form as the quantity of the electric flux, but it's completely different. The electric flux does not really represent something particularly physical. It's a very abstract quantity. So you need to learn how to deal with abstract concepts. We can relate the concept of electric flux to the idea of number of electric field lines through the surface. And we'll do this in a next files. So this is kind of the closest we can come to giving a kind of intuitive idea for the concept of electric flux.